You ever just look up at a massive skyscraper or a sprawling bridge and wonder, how? I mean, really, how do these colossal structures of steel and glass just hang there, defying gravity so effortlessly? It's almost like they're in a constant, silent battle against these invisible forces. And spoiler alert, they're winning. So let's pull back the curtain on this invisible battle and figure out exactly how they do it.
We're going to get to the bottom of that one simple but huge question. Because the answer isn't magic. Nope, it's a brilliant field of engineering built on one single core principle.
And here it is. This is the engineer's golden rule. Seriously, everything we're about to talk about boils down to this one simple idea. On one side of the ring, you've got resistance. That's the structure's built-in strength. And on the other side, you've got loads, all the forces trying to knock it down. For that building to stay standing, resistance has to win, every single time.
Okay, so to understand the hero of our story, the structure's resistance, we first have to get to know the villains. What exactly are these loads that it's constantly up against?
Well, there are a whole bunch of them. You've got the dead load, which is, believe it or not, just the building's own mind-boggling weight. Then there's the live load, and hey, that's us. People, cars, furniture, you name it. And of course, you have the forces of nature, the relentless push of wind, the surprising weight of rainwater collecting on the roof, and the violent shaking from an earthquake. Each one is a pretty tough opponent on its own.
But here's the kicker. Structures almost never face just one of these things at a time. The real trick is designing for the absolute chaos of them all happening at once. Think about it. A windy day during rush hour in the middle of a heavy rainstorm. Engineers have to plan for that worst-case scenario.
So to get ready for that fight, engineers do something really clever. They don't just design for the forces they expect. They use what are called load factors to multiply them, basically cranking up the difficulty. They're designing the structure to fight a supervillain version of reality, a battle against forces that are way more powerful than will likely ever happen. It's all about building in a massive margin of safety.
So, if those are the supersized loads you're up against, what material do you choose to be your champion? Well, more often than not, the answer is steel. Let's take a look at why.
Steel has some legitimate superpowers when it comes to building. It's got this incredible strength-to-weight ratio. But you know what? Its most important feature might just be something called ductility. See, unlike a brittle material that just snaps without warning, steel will bend and stretch and deform first. It basically gives you a heads up that something is wrong. And that warning? That's a crucial, life-saving feature.
And when you put it head-to-head with something like concrete, you really start to see the trade-offs. Steel is lighter and it lets you build way faster, which is a huge deal for tall buildings. Sure, concrete is more fire-resistant, but steel's combination of strength, predictability, and speed makes it the undefeated champ for so many of these huge structures.
But get this, the material itself is only half the story. A solid block of steel isn't nearly as useful as steel that's been given the right shape. I mean, take the classic I-beam. It's a total masterpiece of efficiency. It puts most of the steel on the top and bottom where the bending forces are the strongest and just uses a skinny piece in the middle to hold them together. It's all about getting maximum strength with minimum material. Just brilliant.
All right, this brings us to the real heart of the design philosophy. And it might sound totally backwards, but the secret to making something incredibly safe is to spend all your time thinking about all the ways it could break. You only achieve safety by first understanding failure.
Engineers call these potential ways to fail limit states. You can think of a limit state as any condition on a checklist that you absolutely, positively do not want to happen. A beam bending too far, a column buckling, you get the idea. The entire design process is basically going down that checklist and making sure the structure has more than enough resistance to prevent every single one of those from ever happening.
So, what's on the checklist? First up is yielding. This is when a piece of steel gets stretched so far that it doesn't snap back to its original shape. Kind of like when you overstretch a rubber band. The structure might still be standing, but it's permanently damaged, which means it has failed to do its job.
Next on the list is fracture. Now this one is way more catastrophic. This is when the steel actually cracks and snaps apart. This is that sudden, brittle failure that engineers work so hard to avoid. That's why they love ductile steel. It's going to yield and give you that all-important warning long before it ever gets close to fracturing.
And finally, there's buckling. You know how when you try to crush an empty soda can, it doesn't just get shorter, it suddenly crumples and folds sideways. Well, the same exact thing can happen to a steel column if it's too thin. Even though the steel itself is super strong, the shape can just become unstable when you squeeze it.
So we've designed our beams and columns to be unbelievably strong. We're good to go, right? Well, not quite. A structure isn't just a pile of steel beams. It's a system, and that system is held together by its connections. And as they say, you're only as strong as your weakest link.
Now, the two main ways to connect steel are by bolting it or welding it. You can think of bolting like a massive high-tech Meccano set that gets assembled right there on the construction site. Welding, on the other hand, actually melts and fuses two pieces of steel into one solid part, a process that's usually done with incredible precision back in a factory.
And here's the key. The connections themselves are designed with the exact same philosophy. Engineers identify all the limit states just for the connection, like the steel plate itself yielding or fracturing across the bolt holes, or even a whole chunk tearing out in what they call block shear. And then they design the connection to be stronger than all of those potential failures.
And don't you dare underestimate these little guys. A single standard high-strength bolt, maybe about an inch thick, can handle 120,000 pounds of force per square inch. That is an unbelievable amount of strength packed into some of the smallest parts of the entire structure. They are absolutely critical. Okay, so let's bring this all back home. We started out by asking a simple question. How do these massive things stay up? We've looked at the forces they're fighting and the champion material we use to fight back.
And the answer is that a structure is never really still at all. It's in a constant, dynamic, invisible battle. Every single second of every day, its calculated resistance, in its material, its shape, its connections, is pushing back against all those supersized loads from the outside world. It's a perfect, tense, and beautifully calculated balance.
So the next time you walk into a big building or drive over a bridge, just take a second, look at the steel. It's not just sitting there, it's fighting for you, it's winning. And it kind of makes you wonder, right? What other invisible battles and brilliant designs are shaping the world all around us?